All right, now getting to the more important stuff. So last unit, this is me just picking y'all back up from the previous unit. This all looks familiar. So how do we know by looking at that atom that it is a lithium atom? The number of protons. Okay? So you need to be able to look at your periodic table and still be able to take a look, know what the atomic number means, know what the mass number can get you. And a quick review on that is the atomic number tells you in a neutral atom, neutral, sounds like a test question, in a neutral atom, the number of protons and electrons are the same. It's the same as the atomic number, only in a neutral atom. If it's an ion, it's going to be different. At the average mass number that we're looking at tells you the total number of protons and neutrons. It's the average mass of the nucleus. However, if I said take that number and tell me how many neutrons, there's 2 steps you got to do. What's the 2 steps?
Subtract.
What? Not that one first. That's the second step. If you subtract from that, you're going to get a decimal. What do you got to do first? Round. Okay? Round first to a whole number, and then subtract. All right. So, by the way, I told y'all last unit that we talked about 2 guys, and, well, now we got to actually talk about them a little bit more. They're very important, 2 important people of the periodic table. This is all about the periodic table, by the way. That's why I kind of like this unit. So the periodic table did not always look like this. Can you imagine what it did look like starting out? So this is actually what Mendeleev's periodic table is, a snapshot of how it used to look. And if you take a look, there is no atomic number. In fact, there's only just kind of the mass number. What was the only kind of device he had at his time? A scale or a balance. So he actually weighed these guys, and actually you'll notice that he decided to start seeing empty blocks where he noticed there was a pattern. And so that's where they ended up starting to investigate and discover other elements. So yeah, he started actually putting ones with similar properties in the same column. So he did start out that way. But he also noticed some of the masses started changing a little bit. Keep in mind, he did not know about isotopes at this time. So that's why he started getting weird numbers. You might see like a comma there by the other number. That's him getting 2 different measurements, but he kept them close together until he was able to figure it out. But you need to know this, that he invented the periodic, he started out the periodic table. I don't want to say he invented, but he organized it mostly by atomic mass. And that is a key note right there. There's two people that organized the periodic table. He did it by atomic mass. The other guy we're going to talk about that we already talked about last unit, he did it by atomic number. But they didn't know about the number quite so soon yet. I'm pretty sure he would have done it too. In 1913, though, about maybe 40, 50 years later, Henry Moseley then took the periodic table, reorganized it by atomic number. He did not have to change very much about the organization. Because if you'll notice, as you go up in atomic number, what also happens to the mass? It goes up also. So he didn't have to do very much in terms of changing it. He actually had to only flip some of them around. There's about 5 to 7 elements up there that would swap places with each other in Mendeleev's periodic table. And you can actually look at them and kind of tell what some of them are by glancing at yours. 2 of the ones that come to mind right off the top of my head is nickel and cobalt. You'll notice that cobalt is listed before nickel, even though cobalt has a higher mass. In Mendeleev's periodic table, they would have been flip-flopped. But how did this guy do it? Well, he shot X-rays basically at his doing his analysis, that which was able to give him the atomic number. So after they were actually able to find the number of protons and use that as the atomic number, that's when they actually started going by that in terms of organized periodic table. Also, it's a whole number. It's a way easier to organize it by. Can you imagine actually having to do this with decimals? Ugh.
Ew.
Exactly. All right, so I'm sorry, the name of this unit is actually, it says trends in the periodic table, but that revolves around this one note right here. The periodic law. Basically, when we organize elements in order of increasing atomic number, like Moseley did, we start noticing patterns in their physical and chemical properties. I did not read that off the board at all. I basically know it. And you just need to take it and put it in your words. Rearrange that sentence. That's just a definition I gave you. You could take it and put it in your words. The main 2 things you need to know is that when we arrange them in atomic number, okay, we get a pattern in their physical and chemical properties. All right, so anyway, basically, how do we organize these things? Well, we talked about this briefly last unit. See, a lot of this is just building upon the last one. There are 18 groups and 7 periods. Periods go left and right. Those are your rows. Groups go up and down. All right, so another thing, this is going back to the previous unit. Know the number of valence electrons. The A's, the 1, 2, skip a few, 3, 4, 5, 6, 7, 8. Elements in a group are similar chemically and physically because they have the same number of valence electrons. So going back through each one of these things once again, and this is, again, another good review. Elements in a period are only similar in number of energy levels they have. The first period has 2 elements, 2 and 3 have 8, 4 and 5 have 18, 6 and 7 have 32. That should be really familiar from that chart y'all wrote down last unit. So how can you figure out that number? Where am I getting the number? Well, it's how many elements are in that period. Notice that the lanthanide and actinide series actually fit into the 6 and 7 periods. Again, stuff from last unit where he talked about. By the way, as y'all color, I already mentioned this, y'all are about to actually start organizing your periodic table a little bit, dealing with trends. You might want to write these also on your green one so you can kind of see some patterns. I'd have to give you multiple ones because some people, you put it all on one periodic table, people get cluttered, and they don't like it. And I'll blame you. All right, so more importantly, we now got to get to, this is new material. Everything else that we just talked about was Unit 2. This is actually a new part. So what I'm going to do, there are many trends of the periodic table, but there are 3 main ones. Let's always go with 3. There's always a big 3. So I'm going to show you each one of these trends. Some of them correlate, and some of them are opposite. But they all come together to get this process of a pattern to what developed our periodic table we have today. And y'all are actually going to do a lab Friday, which is based on all of these little trends. Okay, so trends of the periodic table. Many properties of the elements change in a predictable way as you move across or up and down the periodic table. These trends are general. There are a few exceptions because of, well, stability and things like that. And noble gases, since they're stable, they don't fit some of these trends. So you're going to hear me tell you to exclude them because they don't fit the trend. They're not very reactive. They'll fit one, but some of the others are not going to fit. All right, so let's take a look at this first trend. So on your wizard periodic table and also on your green one if you want, but mainly on your wizard one if you want to do this, what I would do is actually, you see how they're drawing the arrows on the periodic table? I would draw them off to the side. So anyway, what is this trend? Atomic radius. By the way, they have the word increasing written up there. That's how it increases. As you go down a group, that's what the arrow means. So if you go down any one of these groups, the atomic radius is going to increase. Okay? Even though you're going down, it is increasing. So it increases as you go down. And I'm going to draw this up here, going to erase it. I use the letter I to represent that. It increases as it goes down. And you can write that on the periodic table if you want. Or you can write the word increase. I don't really care. But it also increases as you go from right to left. The down makes sense because you're adding more what as you go down? Think what else that correlates with on your periodic table.
Shells.
Shells. You're getting another shell every single time or another layer every single time. It makes sense that the radius is going to get bigger as you go down. You know, you're adding another ring every single time. There's one, there's another, there's another. Wow, that's getting bigger, isn't it? By the way, if you haven't figured that out, that's radius. Radius is from center to outside. In an atom, it's from the center, the nucleus, to the outermost electron. Well, if the outermost electron's free floating around here, that's going to be a bigger radius. So let me give you an atom here. So what's really going on is this. You agreed that level 1, level 2, level 3, level 4, level 5, yada, yada, yada. Okay, you got that. All right. Well, here's the thing. As you shove more electrons in that same level, so that's me taking more electrons and shoving it in that same level, why would the radius start to decrease as you shove more in? What's making it contract?
Positive and negative.
Okay. So these guys are negative.
Positive and negative are attracting each other.
And these guys are positive. So you're adding more protons and you're adding more electrons, therefore there's going to be more of an attraction going on. It's not until you reach that next level does it get bigger. So what's really going on as you increase in atomic number, it's just like the typewriter. And y'all did it in your electron configurations. Every time you reset, started back over to the S block, that's when it jumped up to that next level. So what's really going on is this. As you throw in another electron, as you did those 1 through 60, this is what it really happened. You started throwing them in the same level, and it got more contracted until you jumped up to the S, and then it started doing this again. And then it did it again, and it did it again. Every time you hit an S block, every time you hit like 1S to 2S to 3S to 4S, it'll jump back up and then it'll constrict back down. So what's going on is that's why it would decrease as it goes across. You're shoving electrons within that same level. So, okay, atomic radius, by definition. The main thing is you need to know the trend, but you do also need to know the definition. Atomic radius is the distance from the center of the nucleus, that's where the protons are, to the outermost electron, which are negative. The radii increases as you go down, okay? Visually, words, matching, okay? And then decreases as you go across. And what they mean by across is we're in America, we go from left to right. But it decreases. Now hold on 1 second. So that's their word definition. Let's go back to what you just colored down. And this is a good test question. Are they the same? Yes. Y'all are the first group to ever say that correctly. Everybody goes, no, the arrows are not matching. It doesn't matter. So what I could do on the test is the trend is ultimately increase as you go down, increase as you go left. And I always remember, you remember things better in terms of positivity. That's why I'm showing you that. Increase, good, better, going up. Your average, what should be. So that's why I'm telling you, remember it this way. By the way, the element that has the highest radius, you do need to know him. Francium, or as the British say, francium. Okay? You do need to know he has the highest atomic radius. If you remember him, you'll know the trend. Because where is he located? Bottom left. If you remember that, you'll be fine, I promise you. So here's the thing. If you flip the arrows, as long as you change the words, in other words, if I'm decreasing as I go this way, if I turn back around, then I'm therefore increasing. They will do that on the test. Okay, they'll give you more, they like to put it in terms of more like this guy. Just like what you just wrote down as the definition. They try to get you to memorize it like that, but people get confused. So atoms get much larger as you go down a group because you're adding the energy levels. That goes along with the periods of the periodic table. Yay. However, atoms get a little smaller as you go across because you're shoving electrons in that same energy level. This is causing more of an attraction, therefore it's going to shrink until you jump up to the next level. That's also a reason whenever you get to start using noble gas configuration, that's basically you jumping up. When you use a new noble gas, you're jumping up to the next level. The only reason why you think it should get bigger as you go across, because you start writing more electrons within that same level, but actually it's getting tighter. So as you go across, they get smaller and smaller and smaller until you get to a noble gas. So here's my thing, guys. Does the noble gases follow this trend?
No.
No, they don't. They do as you go down, but they don't as you go from left to right. So we kind of exclude them from this trend. Keep that in mind. They do as you go down, but they don't as you go, well, to the other side. All right, so now ions. This is a subnote to atomic radius because what atomic radius is assuming the atom is neutral. Okay? In other words, same number of protons as electrons. But what happens if they're not the same? What if they decide to go into their charge? This is where it gets a little backwards from what we just talked about. It does increase as you go down. However, don't try to look at it in terms of go left and right. Please don't. That's what screwed me up. If you need to think of it like this, you're keeping the protons the same. You're either adding electrons or you're removing them. Well, if you lose electrons, you become positive, which means you're going to also become a lot smaller. And just remember this, if you're positive, you're small. Okay, if you're negative, then what are you going to be? big. So, guys, in case you haven't realized this, a lot of the trends in the periodic table, if you know one of those and you just set on heart on knowing just one of those trends, the total polar opposite will happen for the other guy. So if you're removing electrons, you're going to get smaller. That makes sense. You're plucking things out. Okay? Now, this is a picture. Now, don't freak out when you see this, okay? These are two halves put together. Look at just one element. Pick one. Potassium. Let's look at potassium. Okay. The one on the left is the ion form, okay, which means positive. It forms a positive ion, right? It's in the +1 group. Well, it's over there. It's in the +1 group. Neutrally is the gray. So if it had its full number of electrons, it'd be the guy on the right. Okay? With me so far? Okay, when it loses an electron, it's going to shrink. All of these guys are going to shrink as they lose electrons. Okay? That's the big catch. That's it. What? Because you're removing electrons. The shell is going to get smaller as you start plucking them out. And remember, though, the protons are staying the same. Okay, you're not increasing an atomic number or anything. You're staying with one element and you're plucking them out. As I keep removing more and more electrons from this guy, he's going to get smaller and smaller. That makes sense. That does not follow the same trend as the other guy. So I'm telling you right now, they are two separate trends. Don't get them confused. Because atomic radius and an ion radius is two different things. They're kind of opposite of each other. Good job. All right, so the next one is this. If an atom loses electrons, they become positive, getting smaller. However, vice versa, if you start throwing in more electrons, they're going to get a little bit bigger. And that makes sense. You're trying to shove them in that same level. However, it's not really going to make it any smaller. It's actually going to make it bigger. Again, yeah, it's total opposite from the atomic radius trend. My advice to you guys is think of them as two separate things. Throw more in, you get bigger. So now, however, this picture is not like the last one. You'll notice that the gray is now on the left and the negative is on the right. Okay, so the gray one again is neutral. All right, as you throw more electrons in, you'll notice they get a little bit bigger. Please don't think of these as, you know, peanut M&Ms where, you know, you ever bit half of the chocolate off and you got the peanut in the middle? Yeah, you know you did it. I used to do it too. But let me jump back to the other guy. There's that one. Notice the gray is neutral. They get smaller as you lose electrons. And as you gain electrons, you get bigger. Yada, yada, yada. Okay? Total opposite from the other trend. All right, so trend number 2. That was the first trend. We're going to talk about this next trend, ionization energy. Let me zoom in. So one thing you need to know from the last trend is that noble gases do not follow the atomic radius trend. They do follow only one trend, and this is the trend. What does ionization mean? Ionization, just like they talked about, we watched that little video with the guy, he had the Geiger counter, he was talking about ionization. It's basically ripping electrons off of things, which can be good and yet bad at the same time. Well, this trend right here just shows you the energy it's needed to take to remove those electrons. It takes more energy to snap an electron from helium than it does from francium. Again, total opposite trend from atomic radius. Well, this should make sense. Okay? Why is it easier to steal an electron from francium than it is from helium? Well, it has one valence. That is one, yes. All right. So this is all +1 group. It's easier to steal one from this guy. Okay? Here's another thing. He's all the way down here. He's huge. His electron is way out there. Helium's is in that first level. It's right up close right here. Is it easier to steal something from somebody who's far away from something or if they're right up close to it?
Right up close. Oh, never mind, far away.
Right. So in other words, if the person's looking the other way, you can snatch it and walk off and not have a problem. However, helium, it's like he's got two hands on both of his stuff at all time. You can try to take it, but it's going to take a lot more energy to get away from it. Francium, however, you can steal electrons from him all day. He'll be like, hey, stop that, stop that. No, give it back, give it back. And it'd be like he's get picked on all the time. The reason why is that his radius is just so big. Okay? And all these guys are going to have the same trouble, but he's going to have the most because he only has that one valence electron. Now, as you start stealing more electrons, don't you think the energy is going to go up? In other words, it's going to take more energy to steal other electrons. But I will tell you, this guy's very easy to get it from because he's also the biggest. So therefore, if you're following this trend, increasing as you go up and to the right, then who has the highest ionization energy?
Helium.
We are including noble gases on this one, so it is going to be helium. You need to know helium has the highest ionization energy. If you know that, you got the trend down pretty well. By the way, there's an element for each trend, a different one. None of them are going to repeat. So ionization energy, and I'm going to show you the note real quick, all has to do with the energy necessary to remove an electron. Ionization energy trend does include the noble gases because they have it very stable with 8 valence electrons. Hey, guess what? If you're a noble gas and you have all the electrons, you have all the money in the world, you're not going to want to give it up. So those are going to be the hardest guys to steal electrons from. And it's true. Out of all the periods, they are the toughest. So good luck trying to get it from them. You can do it, it just takes a lot more energy. Okay, so definition. Ionization energy, energy needed to remove an electron from an atom. The definition is it decreases as it goes down, all right, and then increases as you go across. Again, is that the same trend as the picture you just drew down? It is. All they did was flip this arrow and put decrease. I can flip this arrow back and make it go up, but I have to change that to increase. So why? Well, I already told you why, but this is just another good review. There you go. Ionization energy increases across because the more valence electrons it has, the more it wants to keep them. AKA, they want to be like a noble gas, which has that nice full H shell. So if you get that H shell, you're not going to want to go away from it. So anyway, ionization energy decreases as you go down because they're getting further away from the nucleus, so it's a little bit easier to steal them when they're a little bit further away from the creamy filling. Next one, last trend. We exclude the noble gases in this one. This one's called electronegativity. I like this one a lot. By the way, you should notice something similar to the last trend.
It's the same.
It's the same. Guess what? It's harder to remove an electron from guys that are in the upper right-hand corner, but also the reason why those electrons want to stay a little bit more tightly to that is that these guys are a lot more attractive. We exclude the noble gases from this trend because, well, they don't really fit the up and to the right trend. So therefore, who has the highest electronegativity out of the entire periodic table? Fluorine. He has the highest. By the way, on your green periodic table, it's good to pinpoint this out. Look for, you might notice, look for electronegativity on your periodic table. Look at your little thing in the top middle of your periodic table, you'll notice something. You'll notice that there is an extra number some of y'all were asking me about at the beginning of the year. What's the 2-digit number that's down there in the bottom right? That's electronegativity. It goes all the way up to 4.0. Who has a 4.0? This gal. She is the most attractive element off the entire periodic table. Yes. Yeah.
So like, they can't be noble gases?
Cannot be noble gases, right. They have a full shell, so they're not really being attractive. They're not losing or gaining electrons, so they're, you know, whatever. You'll notice this. As you go across, you are getting more valence electrons. You're also becoming more negative. But it is the most attractive. The reason why, everything wants to bond with it, and it's ripping things apart. But anyway, there's more about that later. All right, so if fluorine is the most attractive, francium is the least attractive. So best way to kind of look at this and why I like this so much is this. These guys are going to give up electrons over here. These guys are going to take them away. That's why that trend's so important. So electronegativity, it's basically, well, stealing electrons. All right, let's get into some definitions. You got it up and to the right, yada, yada, yada. All right, Electronegativity is the ability to attract electrons in a chemical bond. Electronegativity, aka E-neg, I don't know why, but that's what they did instead of IE, are numbers without units. Fluorine has the highest, which is a 4.0. It's kind of like your grade point average, except for attractiveness. All right, so quiz time. Which element has the highest ionization energy? Helium. All right. Second question. Which element has the highest atomic radius?
Francium.
Francium, okay. And which element has the highest electronegativity? Fluorine, okay. Those three elements are very important for this next test. But anyway, electronegativity, if you'll notice also, as you go right across the periodic table, if you exclude the noble gases, you become more negative. And if you go left, you become more positive. So that's why it's called electronegativity, electrons going to the more negative side. That's why it's called electronegativity. Electronegativity, the definition is very simple. It decreases as you go down a group and increases as you go across the period. It is exact same trend as ionization energy, but what is the difference? They do not include the noble gases in electronegativity. We include them only in one trend, and that's ionization energy. Anyway, we start noticing a pattern when we actually overlap all three of these guys together. And we also notice a fourth trend. This is a hidden trend, but this is one you're going to naturally have to know. Oh, by the way, in case you've been asleep the past 30 minutes, that trend right there summarizes all four trends together. I said there were three, but there is another one in terms of metal, non-metal, and metalloid. So when we do overlap all three trends together, we get to see this little pattern. We start noticing that the metals, non-metals, and metalloids all kind of follow like a magnet, or like a bar magnet, or a battery if you want to look at it that way. The metals are mostly going to be on the left side. They're going to follow the atomic radius kind of deal. But as you go off to the right, you're going to end up becoming more electronegative, or actually more like a noble gas. Or, I'm sorry, let me rephrase that, more like a non-metal. Sorry, the ends messed me up. So this is a great summary. This actually summarizes half the entire unit just by looking at this one thing.